Howdy, folks. Welcome to CS128 Honors. Today, we are doing a quick review on ownership and borrowing, and also an introduction to slices. First, what is ownership? So each value in Rust has a variable called its owner. There can only be one owner for every value at any given moment. And when an owner goes out of scope, the value is dropped. So here are two examples demonstrating the concept of ownership. On the left, we see that the string W containing the string value word gets dropped when it goes out of scope. That is when this curly braces end. And also the string S, which contains the string value hello, which goes out of scope when the scope, that is a function main, ends. And on the right is an example of moving. So we have a string S containing the string value hello, and its value is moved to the string Y. So we can no longer do anything with X. If we try to print X, the code will not compile. And what is borrowing? So at any given moment, we can either have one mutable reference using ~mut, or an infinite number of immutable references using plain ampersand. This is very important to keep in mind. A mutable reference must always refer to a mutable variable, of course, and references must always be valid. And here's an example demonstrating ownership, demonstrating borrowing. We have the string mut, that is of the containing the string value hello, and then we create a mutable reference to it in the variable y. Now, if we try to push to string x, this code will not compile. That will be an error because this function push string requires another mutable reference to x, which you cannot have since we already have one in the variable y. So this code will not compile. Let's look a bit at data structures. So data structures such as vectors or strings, they contain values you pass into them. A typical implementation of a data structure has a data or a collection of data on the heap, a pointer to set data on the stack, and record keeping variables such as size or capacity also on the stack. In Rust, one thing to keep in mind is that data structures own values. They own values you pass into them. So say you pass a string into a vector, then the vector will own the value in the string. An array, as you may have known from an earlier lecture, is a contiguous collection of type T objects and with a size n known as compile time. Hence the type signature here. We have type T followed by the size n. Every array live on the stack. At least the arrays that we can interact with, they all live on the stack. What are slices? So suppose you want to get a subarray, that is a section of an array, and you want to borrow from it. Well, slices allow you to do just that. They allow you to view into or immutably borrow any contiguous collection of type T. Hence the type signature here. We have an array notation containing the type T and an ampersand, signifying that the slices is essentially a immutable borrow. The original collection of type T can live anywhere, can be on the stack. So our array, the array that we can use, or it can live on the heap, as we will demonstrate later. The size of slices are not known at compile time, meaning they are determined when the slice is actually created. And as we mentioned, slice is allowed to borrow a section of an array or a subarray. Here's an example. We have an array X containing objects of type I32, and the stack has size 5. The values are 1 to 5. First, we create a slice to the entire array X. So what we do is that we declare variable x slice, x underscore slice. That is, it will be the type slice into a collection of iterations. Do note that the type looks exactly as if we just borrowed from the array, an array of i32s, because that is essentially what we are doing. And then we create the slice by just borrowing from x. That creates a slice. So how do we create a slice to a subarray? Well, we do something similar. We declare the variable. The type will also be a slice into a collection of i32s. And instead of just %x, that is borrowing from x, we do a borrow of x, but only from indices 1 to 3. So this range notation 1.4 means indices 1 to 3. And so the result is that this variable x slice section here will contain a slice only to indices 1 to 3 of the array x. Note that since we already have two immutable references here, if we try to assign to x, the code won't compile because it is already borrowed. And if we try to print out x slice, it will just print out the entire array x. Slices can also interact with vectors. Vectors, as also introduced, are also a contiguous collection of type T objects, except this collection is mutable. And as we see from the notation here, we have a vect and containing type T's. A vector have mutable size, which is not known the compile time. And a vector, as we already saw from our review on data structure, stores a collection of data on the heap. In this case, an array on the heap, a heap array, whose size is also not known the compile time either. So it's not very similar to the array we saw from earlier, which has a with list on the stack and have known size, but that is also an array. And slices can also borrow from the heap array, from this heap array. This borrow is also a borrow of the vec itself. And this is an example. We have a variable x that is a vector of i32s and containing the values 1, 2, 3, 4, 5. This vec internally also stores a heap array containing values 1, 2, 3, 4, 5, of course, on the heap. And if we try to create a slice that borrows from x, how we do it is basically the same as if we just borrow from an array. We do x underscore slice. The type is a slice into a collection of iterations, and we just do %x. That's a borrow. This borrows from x and also borrows from the heap array. And what if we wanted to create a slice into a subarray 1, 2, 3? Well, the code is also the same. We have the variable of the type slice into iterations, into a collection of iterations. And we also do a borrow of indices 1, 2, 3. Similarly, from earlier, if we try to assign to x, it won't work because we already have two immutable references here to the vec or to the heap array contains. And so an assignment won't work. Now let's look at that example in code. Here you can see the similar example. We have the same array x from the same vector x from earlier, and we create a slice from x. Do note that we wrap it in curly braces so that as we exit this scope, x slice will get dropped, so we will no longer have a reference. After we take the slice from x and assign to x slice, we try to printing it out. After that, we assign index 3 of x, the value 6. And we try to take a sub array or subvector or whatever, a slice into indices 1, 2, 3 of x. And then we try printing that slice out. Let's see what actually gets printed here. So actually the first print is the slice x slice here, x underscore slice here. As you can see, since we borrow the entire vector x, that entire vector will be printed 1, 2, 3, 4, 5. And this second print is the variable x underscore slice underscore section. As you can see, we only borrow indices 1, 2, 3. This slice always only views into indices 1, 2, 3. So only those indices will be printed. And since we already assign 6 to index 3, we will print out 2, 3, 6, not 2, 3, 4. Here is a diagram demonstrating how that example actually works in memory. So as you can see, we have the vector x here. The stuff below x, this board is everything that lives on the stack. We have 3 members that live on the stack: a pointer, that is a pointer to the array on the heap, and various variables for length and capacity. At this moment, or both of them are 5, since since our vector has length 5 and capacity 5. And we also have an array on the heap with 5 indices and 5 values: 1, 2, 3, 4, 5. And the pointer of the vector x points to this array on the heap and allows the vector x to own this array. We also see the variable x slice here. It is a slice. You can think of a slice as a pointer to the contiguous data and a variable for length. So as you can see, since x slice borrows from the entire vector x, the pointer will point to index 0 of the heap array, and the length will be 5. So it allows us to view into all of the 5 elements of the array. And we also see the variable x slice section here. Since our view or our borrow only starts at index 1, the pointer will point to index 1 instead. And we have the variable length is 3, meaning that we can view 3 elements. So element 1, element 2, and element 3. And do note that even though all 3 variables point to various places in this heap array, only x actually owns it. All the other 2 are just borrows. And the Rust compiler will check that it is valid. These borrows are valid, meaning the borrow pointers don't point to invalid addresses. And only x actually owns this array. Now, in our lecture about string, we introduced 2 types of string: the string with capital S and the &str. In that lecture, we just said that the differences are the &str is immutable and the string is mutable. And here we also see how to create these 2 types of string. For the &str, we just encapsulate a string inside double quote. And for a string capital, there are various ways to create it. We can do a string : from and string inside capital inside double quote, or do a string double quotes dot to underscore string. We also saw a way of creating an &str from a string capital. That is just call the function s underscore str on the string capital. So is that it? Is this all the differences? Obviously, the real deal must be more intricate, right? And why does &str has an ampersand in it? Well, as it turns out, the formal definition is that a string capital S is a contiguous collection of UTF-8 characters. That means the characters that can be represented by a maximum of 8 bits or 1 byte. A string, as we already mentioned, has variable size, not on the compound time. What does this sound familiar to? A vector, right? So a string, you can think of it as basically a vector containing the type U8. So why U8? Because we have UTF-8 characters. That means what? That means 8 bits. And the type US also has 8 bits, so perfect for UTF-8. Do note that VecUS is a helpful way of thinking about it, but we cannot actually use vector methods on string. We have to use string methods because strings has a lot of constraints associated with it. Not so it's different from a vector in that regard. Also, what is an ampersand STR actually? Well, it is also a slice, as we may infer from the ampersand. The entire type is actually called a string slice. Similarly to string, you can basically think of it as a slice into a collection of U8, since we have UTF-8 characters. And as you may have guessed, we can use this to borrow from a string's heap array of U8. This is also a borrow of string itself. And similarly to how slices can be used to borrow subarrays, a string slice can be used to borrow substrings. Note that we can only borrow from strings, so not the vector US, but an actual type string. So this is an example very similar to the from earlier. We have a variable x, this type of type string containing the value string hello 628 on this. To create a slice that borrows from the entire string, we also just do the same similar thing from earlier with borrow from x. And that's it. That will create an ampersand STR. We can also create an ampersand STR that views into a substring by just borrowing x from indices 1 to 3. That will also give us an ampersand STR, except it only views into 3 indexes. And then we try to print them out. Let's look at that example in practice. So this is the same code from that example. We have the string x containing the string hello 138H, and we create 2 ampersand STRs by borrowing from x. Let's try printing that out and see what happens. As you can see here, so if we try to print out x slice, since x slice borrows from the entire string x, the entire string CS128, actually this CS128 will be printed out. And x slice substring, x underscore slice underscore substring, since it only borrows, it only views into x from indices 1 to 3, only ELL will be printed. That is index 1 next to index 3. So it works very similar to vector array and the normal slices, except it's string specific. Some of you may have noticed that something is missing here. First thing you may notice is that we have a string analog to a vector, that is a string capital S. We also have a string analog to a slice, that is a string slice. What about here is a stack array? That's the array that we can interact with. Moreover, we had an example of how to create an ampersand SCR from a string. Don't ampersand SCR have to borrow from something? So welcome to yet another type of string, the str primitive type. It is very array-like. So it's basically just a contiguous collection of U8, except unlike a string capital S, it's direct access. So there's no the pointer on the stack pointing to elsewhere. Its size though is not known at compile time. So that is a difference from the stack array. And the SCR can live anywhere. It can live on the stack, it can live on the heap, it can live in the text segment of your code. For example, static strings are STRs that live in the text segment, as we will demonstrate later. And the U8 array stored by a string capital S is an STR that lives on the heap. The STR is mostly seen in borrowed slice form, and in fact, the capital STR type is borrowed from this type. Hence, we have the ampersand right there. Otherwise, this type is very rarely used. In the example of the top, we see the classical way to create an ampersand STR. Well, we kind of lied about you earlier about what this line actually does. It doesn't actually create an ampersand STR containing these values. What it does is that it has a static STR in your type code type segment. And then when this line is run, it creates a slice borrowing from this static STR and then assign that slice to the variable X. And hence X has a type ampersand STR. The example below is an example of an STR that lives on the stack. So we have as a array X here containing 3 objects of type U8. Sounds familiar. That's basically the canonical character type in Rust. And the values are the RC value for the characters A, B, and C. So 97 to 99. Here we create a variable X underscore borrow. That is of the type ampersand STR. So why do we name it X underscore borrow? Well, you can see from the function from UTF-8 here, STR colon from your UTF-8. So can you guess what they do? Well, it basically creates an ampersand STR as we see here. So what this function actually do is that first it treats X as an STR that lives on the stack. So even though we actually have an actual array here, it still treats it as a STR, which is an array anyway. And when you pass in this slice to X, that is, we borrow from X, we have a slice, it converts that slice to X into a string slice. That is the ampersand STR that we assign to X here. And since we don't actually create any new value, we just convert a slice. This X borrow will borrow from X. The borrow checker will treat X borrows as borrowing from X. So later, if you try to do something like X index 0 equal to 1, that code won't compile because we already have an immutable reference to X in the variable X borrow here. And if we try to print out X borrow, note if we print out X borrow, which is the type ampersand STR, the string ABC will be printed because X borrow is a type ampersand STR. And so when we print out borrow, Rust will treat the original contiguous collection as an STR and print the actual characters out. But if you try to print the actual array X out, it will just print 97 to 99. So let's look at how that example actually plays out. First, the example of a static STR. So this is the example we are all familiar with. We create a variable hello of a type ampersand STR, and we have this string here. How does that work? Well, if we look at the program dump, that is the stuff that yes, that appears when after you compile the code, you can see that the string is just straight up stored in the code in the text segment. You see there's a string here, hello CS going to translate honors. Yes, stored in the text segment of the program after compiling. And when this line of code is called, it will create a slice to this string in the text segment here and assign a slice to the variable hello, hence the type %str. So every so it can this slice doesn't actually create the string. It will just create a slice which already exists in a text segment. And if we try printing that out, you see that hello, that string in the text segment will get printed out. And this is an example of the stack string. This is the same example. We have the array X containing 3 U8, 97 to 99, all the characters A, B to C. And we create a variable X model that is an ampersand str. And this slice is converted from a slice to X. There's no new value created here. And here we try printing out X and printing out X model. Let's see what actually happens. So if you print out X, that will just treat it as a normal array. There's no string stuff here. So the array will get printed out 97 to 99, the actual array here. However, if you try to print out X model, since the type X model is %str, when you try printing that out, Rust will think that the original collection is an actual str, and so Rust will print them out as characters. And so Rust will print out the string ABC here because we have the RC values for characters A, B, C, and C here. And do note that this will only be treated as an str, as a string, whenever you use a variable X model, which is an %str. So if we try printing out X again, you will see that the array will still get printed. If we try to use X as an array, if we try to use this string slicer is an actual string. And something to note is that you cannot do this. And let's try compiling that. So it says the compiler says that we cannot assign to X because it is already borrowed. And that borrow happens when we created this %str. Yeah? Even though it looks like it's an ampersand to a different type, it's still a borrow to the array X. Since we kind of treated it as an str and just converted the slice. So yeah, that's basically an introduction to slices in Rust and various rules associated with them.